All right, everybody. We are now going to talk about substitution method. Okay, a way to find particular integrals. So far, we've looked at basic integrals, so how to deal with functions that we know specifically, like ln or e to the x, or things with reverse power rule. But what do we do if I wanted to find the integral of a function that's representative of the chain rule? Remember what the chain rule says. The chain rule is the derivative of a composite function, and it's start from the outside, work your way in. D dx of this is equal to f prime g of x times the derivative of g of x. So if I wanted to integrate this, so in other words, if I wanted to go, the integral of d dx f g of x dx. Okay, so basically I want to get back to the function f of g of x. Okay, by the fundamental theorem of calculus part 1, basically these things just cancel out. How would I actually solve the integral of this f prime g of x times g prime of x dx? How would I do that? Okay, and if we rewrite this, simplifying the left side, we're just going to get this expression here. So we can perform a change of variable. So with a little bit of, switching things up a little bit and writing down what they mean, we can transform this integral into one that we know how to solve, and then we can transform it back into our original variables. Okay, so what we're going to do is I'm going to say, this is the thing that's causing me the problems, the g of x. Because when I look at the derivative, it's then multiplied by the derivative of this function. So what I'm going to do is I'm going to say, okay, I'm going to call the g of x part a new variable u. Now, if I differentiate this expression with respect to x, so if I have du dx, so in other words, g prime of x, and what we do is we write it in differential form. So what I do is I cross multiply my dx, and I get du is equal to g prime of x dx. Now, why would I want to do this in differential form? When we're actually doing these problems, you don't have to do this step. You can jump straight to here. The reason why we're looking at differential form is because I want to isolate for my dx. Du is equal to g prime of x. Now, why would I want to do that? I want to do that because what I can do is I can sub this part into here, and then I can sub my u where my g is. Now, if I do that, what I'm going to end up getting is the integral of f prime, and I'm going to put a u in here now, and then I still have this g prime of x, but then my dx, I'm going to write it as du over g prime of x. And now this simplifies things greatly because my g primes here, they're going to go away, and what I'm left with is a much simpler integral. It's just the integral of f prime of u du. And by the fundamental theorem of calculus, we know that integrals, derivatives cancel each other out. So I can just integrate this to get my f of u plus c. Now, when I'm here, I'm not quite done yet because I have an answer with respect to a different variable. The actual problem I'm trying to solve is with respect to dx. So what I do at the very end is I take this g and I put it back in here. So I'm going to get f of, put this in a different color so it stands out, g of x plus c. Okay, so this is known as the substitution method. And the substitution method is summarized as so. So you pick a variable, the thing that looks the most scary, basically, and then we differentiate. So we go du is equal to g prime of x dx. So we differentiate it in differential form. And then we make the substitution, and then we integrate. So let's just do a whole bunch of examples. And the more of these you see, the easier it'll become for you to do this on your own. So typically when you're looking at a problem, it's really difficult at first to figure out what to do for the substitution. So typically what I ask students is, in here, what looks the scariest? The thing to me that stands out the most is this x squared, because I know that if I take the integral of just e to the x, I'm just going to get e to the x back. So x squared is the thing that's tripping me up, but the other thing is that when you think you know what your u is, when you differentiate it, is that derivative somewhere in your integrand? And if I differentiate x squared, I'm going to get 2x. So those are the two hints that are suggesting that for substitution, we should do u is equal to x squared. So then my du is going to be 2x dx. And if I isolate for my dx now, I'm going to get du over 2x. So now if I put these things into my integral here, I'm going to get the integral of 2x, e to the u, and then I'm going to replace my dx with du over 2x. And now this was definitely a good choice because my 2x's are canceling, okay? And I'm just left with the integral of e to the u du. And I know exactly what that is. This is just e to the u plus c. This was one of those special integrals in the chart that we made. But I'm not done yet because my answer should be in terms of x, not a u. So I need to plug my u is equal to x squared back in to get my answer. Now let's do a quick check to see if this is correct. So if I go d dx of e to the x squared plus c, derivative constant goes away. And for the exponential, we rewrite what we have, and then we take the chain rule. So differentiate the thing in the exponent. That would be 2x. And was this the original thing I wanted to integrate? Yes, it was. So I know it's the right answer. Okay, let's try this one now. Part B. So the integral of 2x, 1 plus x squared. Now again, when you're looking at this, what is the thing to you that's standing out the most or that looks the freakiest? To me, I'm like, oh my goodness, so 1 plus x squared at the bottom here. But then the second thing I'm thinking is if I differentiate this, I'm going to get a 2x. And I'm also seeing a 2x in this integral. So how about we try u is equal to 1 plus x squared. So if I differentiate that, I'm going to get du is equal to 2x dx. And if I isolate for my dx, in this case it's actually the same as it was above, I have du over dx. Okay, so then if I make the substitution, I'm going to go integral. I'm going to leave the 2x alone because I haven't done anything with that yet. But my 1 plus x squared, that's the thing that I called u. And for my dx, we wrote that as du divided by 2x. And this was a good choice because now all my other x's in my integral go away. And I'm only left with u's, particularly 1 over u du. And I also know what this integral is. This was also in that integral table we made. This is just ln. And remember, we're going to go absolute value of u just to be on the safe side to remind people that, oh yes, we can only have positive values of u in here. And then don't forget our plus c. But we're not done yet because I need to have my answer with respect to x. So we're going to plug in our 1 plus x squared again. That's what our u was, plus c. Now, in this case, if you wanted to, because I have 1 plus x squared and x squared is always going to be positive, you can put rounded brackets here. Okay, but if you're concerned that you may miss that sometimes, you can always just put absolute value. Now let's do a quick mental check. Let's look at the ln of 1 plus x squared plus c and differentiate it. So when we differentiate ln, we go 1 over the thing in the ln. And then by chain rule, we differentiate the thing at the bottom, which is just 2x. So is that what I started with? Yep, 2x divided by x squared plus 1. So I know it's correct. Okay, let's do one that's really similar. So now this is the same as above with the exception that the bottom is now being squared. Okay, so if I still pick the same u here, I saw from above that it would cancel out the 2x up here. So that still seems like a good choice. So let's try it. 1 plus x squared, so my du would be 2x dx. If I isolate for my dx, I'm going to get du over 2x. And now I'm going to make the substitution. So I'll have the integral of 2x divided by, now the bottom is squared, so I'm going to have a u squared on the bottom. And for my dx, I'm replacing that with du over 2x. And this is good. All the other x's disappear. And I'm left with the integral of 1 over u squared du. And if I just change how this looks a little bit, if I write it as the integral of u to the negative 2 du, I can now use reverse power rule on this. So I'm going to add 1 to my exponent. So I'm going to get negative 1. And then I'm going to go 1 divided by that new exponent. So negative u to the power of negative 1 plus c. And I'm not done because I need to put my x values back in here. So I have negative 1 over 1 plus x squared plus c. Now, again, if we check this, and I'll write it in the form that it was before. So I'll write it as negative bracket 1 plus x squared all to the power of negative 1 plus c. And if I differentiate this, my negative is going to come down. So these negatives are going to cancel. And then I have 1 plus x squared all to the power of 1. And by chain rule, I'm going to get times 2x. And sorry, negative 2 there. And is this what I started with? 2x over 1 plus x squared all squared? Yes, it is. So I know that it's correct. All right, now let's do one with a ln. Now, if I look at this, the thing that's the freakiest to me is the ln part. Some people may think to try to use this as your u, but that wouldn't be very useful because if I differentiate 3x, I'm just going to get 3, and then I have no way of getting rid of this x. So how about we try the part that looks the freakiest? Let's try ln is equal to 3x for our u, or sorry, ln of 3x is equal to u. So when I differentiate this, remember ln, we go 1 over what we have, and then we're going to use chain rule. So derivative of the bottom, which would just be 3. And don't forget, we need this in differential form, so I need to put a dx here. So my 3's will cancel, and I'll just be left with 1 over x dx. So when I isolate from my dx, I'm going to cross multiply and get x du. Now, let's see what happens if I plug this in. So I'm going to get the integral of, I've replaced the top by a u. Okay, I still have this x here. But now for my dx, I'm going to replace this with x du. And this is great because these x's go away. And now I'm only left with my variable u. And I have the integral of u du. By reverse chain rule, this is 1/2 u squared plus c. But I'm not done yet because I need my answer in terms of x. So I'm going to have 1/2 ln of 3x was the thing that I called u. Remember, this is all squared plus c. And again, let's do a quick mental check to see when we differentiate if we get our original integral back. So by chain rule, this 2 is going to come down here and it's going to cancel out with the half. So I get 2 over 2 ln of 3x to the power of 1. But by chain rule, I got to take the derivative of the stuff inside, which is 1 over 3x. But again, by the chain rule, I got to take the derivative of the bottom, which is just 3. So these 2's will cancel, this 3 will cancel, and I'm just left with ln 3x over x, which is exactly what I started with. So I know that I did the right thing. All right, let's do a couple more. Okay, this one, roots, lovely roots. Okay, so what's the thing that looks freakiest? The stuff in the square root's kind of freaky. If it was just the root of x, I know how to integrate that, but this plus 1 is making me uncomfortable. So let's try to do x squared plus 1 as our u. And this is also a good sign because when I differentiate, I'm just going to have a 2x and I have an extra x here. So that's looking like it's going to work. So if I isolate for my dx, I'm going to get du over 2x. And this transforms my integral into the integral. I'm going to ignore this x. But underneath the root, this is the thing that I called u. And then for my dx, I'm going to have du over 2x. And this is good because now the x's here cancel, but be really careful because I still have a 1 over 2 here. Having a constant left over is not a problem, just don't forget about it. Okay, so I'm going to go integral. I'm going to actually write my constant first, and then I have the root of u du. And now I know how to integrate this. Okay, I'm going to just rewrite it slightly as the integral of 1/2 u to the 1/2 du. And then by reverse power rule, I'm going to have 1/2 u, add 1 to the exponent here. So 1/2 plus 1 is 3 over 2. 1 over the new exponent, so 3 over 2. This just means 2 over 3, but I'll write it on my next step. And then I have plus c. Okay, so I have 1/2 times 2 over 3, u to the 3 over 2 plus c. My 2 on the bottom, my 2 on the top will cancel, so I'm left with 1 over 3. And now my u, I need to put back in what I had. So my u is equal to x squared plus 1 to the power of 3 over 2 plus c. Now let's do a quick mental check. 1/3 x squared plus 1, 3 over 2 plus c. Derivative of the constant goes away. By chain rule, I'm going to have 1, 3. Bring down that 3 over 2. Then I'm going to have x squared plus 1. Subtract 1 from the exponent. Multiply by the stuff inside my brackets, the derivative of that, which is just 2x. And now when I simplify things, my 3 is going to go away here. Oh, I have a 2 and a 1/2, so that goes away. And I'm just left with x squared plus 1 all to the half, which in other words means the root. Okay, which is exactly what we started with. Okay. Ooh, now this one, sine. So what's the thing that looks the freakiest? Definitely the root x, at least for me. Okay, so let's try to take u is equal to the square root of x. Now this is also a good choice because when you differentiate root x, you get 1 over root x. And I'm seeing something like that here. So if I differentiate this, I'm going to get 1/2, 1 over root x, and differential form. So we have our dx here. And if I isolate for my dx, I'm going to get 2 root x du. So when I sub this in, I'm going to have the integral of 1 over root x sine of, this is the thing I'm calling u. And then for my dx, it's going to be replaced with 2 root x du, which is good. This root x gets rid of this root x, but just be careful. We have a 2 left over, so we're going to bring that out to the front. Okay, so we're going to get the integral of 2 sine u du. And now I know how to do this. You can also think about moving the 2 outside if you want. You don't have to. You can leave it inside if you'd like. Now, what is the integral of sine? That would be negative cos. Because if I differentiate cos, I get negative sine, and I'm going to have this extra negative around. So this is going to be negative cos u plus c. Okay, so I have negative 2 cosine. What was my u again? My u was root x. And then I have my plus c. And let's do a quick mental check to see if this will give us the right answer. If I differentiate. Okay, so the constant goes away. I have negative 2. What is my derivative cosine? It is negative sine root x, but now I got to differentiate the thing inside the sine. So the derivative of root x is 1/2 x to the negative 1/2. Okay, so this half here, cancel with that 2. This negative will cancel with this negative, so that goes away. And I'm just left with x to the negative 1/2 sine root x, which in other words means 1 over root x sine root x, which is exactly what I started with. Okay, so I know that I did the right thing. Okay, so we'll do more of these types of problems on Wednesday. Okay, you may have to even watch this video more than once. Okay, substitution is really weird the first time you see it, but try to go through these and think to yourself, which thing looks the freakiest? And then if I pick that for my substitution, when I differentiate, will I get something that looks like the other x portions of the integral that I still have to get rid of? Okay, hopefully you found this helpful. Thank you very much.